with your coordinator so that your coordinator can immediately contact with me so that we can resolve the problem. And also during the session, I will switch off my video to avoid any distractions. Then again, at the end of the sessions, I will switch it on. And again, feel free to ask me questions or to raise your questions during the sessions. I will be happy if you interrupt me during the sessions. So this is optimization techniques and its application. So mainly, I will focus on some fundamentals on optimization techniques, particularly something I will tell some ideas or some observations on maybe on genetic algorithm. And then I will show you that some numerical applications actually, and also how it can be applied to solve some problems. That also we'll try to focus. Now I will share my PPT. So I hope that I'm audible clearly and my PPTs are visible to the participants. So can anyone confirm it? Yeah, okay, thank you. So here mainly I will try to convey the observations or some key ideas behind it. So optimization techniques and its applications, as you know, so once we'll study big data or data science or maybe artificial intelligence or applications, probably each and everywhere you will find out the application of these optimization techniques. Optimization techniques normally play a very critical role, maybe data science problems or maybe AI/ML problems. So I can tell you here one simplest thing. So suppose you are working with a high volume data. Okay. So once you are working with a high volume data, then sometimes what you need to do, so on those high volume data, and you need to maybe do some dimensionality reduction process. You need to reduce the dimension. So once you want to reduce the dimension so that without compromising with the data, the number of parameters may be associated with that process. And again, how to optimize those parameters so that this dimensionality reduction procedures may be a more or less correct one. So another thing I can tell that that artificial neural network, so that is the backbone or pillar. We normally say that for any of this machine learning or artificial intelligence problems, in artificial neural network, again that some weights are there and biases are there, and sometimes what you need to do, many parameters are there, and sometimes so you need to optimize the weights actually. So how to optimize the weights of artificial neural network? Then again we need to take help of this optimization techniques. So optimization means simplest sense I can tell that once we want to maximize something or sometimes we want to minimize something, then you need to do this optimization process. Once this our criteria is cost, then obviously we will go to minimize this cost. We will never go to maximize the cost. And once our criteria is benefit, then obviously we will go for maximizing the benefit. So optimization means it may be either maximization or it may be minimization. So it based or it depends on the criteria, which criteria you want to minimize. Now again, another thing is that simply optimization. Optimization may be of two types basically. One is single objective, second one is multi-objective optimization. And in single objective optimization, what is your objective? To maximize or minimize only one objective. So today the problem that I will try to give you an overview on traveling salesman problem. Let us consider the traveling salesman problem. So if you know this traveling salesman problem, it is fine. Otherwise, let me explain what is traveling salesman problem, then probably things will be much more clear. So, in traveling salesman problem means I want to say this is TSP. In briefly, we say TSP. This is called traveling, T for traveling salesman, P for problem. So, traveling salesman problem. So, the problem itself, I think, is self-explanatory. So, here, a number of cities are there. So, suppose these are the number of cities. Okay. So, these are the number of cities. And a salesperson is there, or travels person is there. So, what is the objective of this travel person or salesperson? So he or she need to visit all these cities like that. So visiting all these cities. Let us say he is visiting all these cities in this manner. Let us assume, okay, visiting all these cities and then coming back to the initial city where started the visit. So see that in the process, all other cities except the initial city, it is restricted that he or she will visit at most one time. But the starting city he may visit, because once is visiting, starting, and again once closing the visit, again coming back to the initial city. So let us say this is city 1, this is city 2, this is city 3, this is city 4, this is city 5. Okay, so let us assume here that all the cities are connected with each other. Let us assume. Now, what will happen here? So, what should be the optimum schedule once the traveler or salesperson starts visiting the city from the starting node, so that each and every node in the city except the initial or starting node should be visited only one time. So what do you want to do here? So you want to optimize the cost. So once that salesperson is visiting the cities, so our objective is that, okay, we will optimize the cost. That means if this is our objective, we want to optimize the cost. Now see, here objective is only one. We try to optimize the cost only. Objective only one. So this is called single objective optimization. And if the objective is that, okay, I want to optimize the cost, again, I want to optimize the time also. See, here, firstly, what I am telling, in first term, I am telling that in this traveling salesman problem, initially, the salesperson will try to optimize the cost. As I told, cost optimization means obviously that is cost minimization. So once we want to minimize the cost, we are not considering any other criteria. We are considering only one objective. That is, we want to minimize the cost. Okay, that is single objective optimization. Here, we have only one objective. Okay, but if we consider another objective, let us assume cost be or another objective, time be or another objective. Then suppose, so I want to visit all these cities, come back to my initial city. I want to optimize the time also. Time optimization means what? Time optimization means obviously we'll go for minimizing the time. We will not go for maximizing the time. See. So once we will consider these two criteria or these two objectives, one is cost, second one is time, then I am telling this kind of problem is known as multi-objective optimization problem, where number of objectives will be 2 or more, and often, once number of objectives are 2 or more, so that is, and the objectives will be in conflicting sense. Objective will be conflicting. Now, see the situations. So as I was telling that once, in traveling salesman problem, you want to minimize the cost and we want to minimize the time. How it will happen, just to tell me. So if we want to minimize the time, how cost can be minimized? Is it possible? If you want to minimize the time, that means, you need to travel maybe by flight. So since you want to minimize the time. But once you are traveling through flight, then can you minimize the cost? Obviously, then you cannot minimize the cost. Okay. So now the thing is that if you want to minimize the cost, then what will happen? So if you want to minimize the cost, maybe then you should travel through bus or some other means. Okay, where cost will be minimum. But once see that if once cost is minimum, can you compromise with the time? Cost is minimum, means time will be maximum. You're getting, so these two criteria, what I am telling, that time and cost. So these two criteria are conflicting with each other. If you want to minimize the time, then cost need to be maximized. And if you want to minimize the cost, then time will be maximized. Okay, so how to proceed in this kind of situations? So try to understand. I am telling that optimization problems may be of two types. One is single objective optimization. Second one is multi-objective optimization. Single objective optimization, only one objective will be there, and in case of multi-objective optimization, we need to deal with two objectives. So now, what we see in the real life, whatever the problems we will get. So all the problems are multi-objective in nature. Very few problems we will find out which are single objective optimization problems. But again, we should have the idea of these single objective optimization problems. So then only we will get to know how the multi-objective optimization will work. And again, one more thing I want to convey, that once we solve single objective optimization problem, you will get only one solution. But once you will solve multi-objective optimization problem, then you will get a multiple number of solutions. Then your question may be, sir, how from those multiple number of solutions we will select one solution? Yes, from those multiple number of solutions, based on your domain knowledge, you need to select which one is the better one. Because you are feeling the point. If I want to minimize the cost, if I want to this cost and time, both I want to minimize, obviously then I will get a set of solutions, set of compromise solution, better I should say. I will get a sort of compromise solution where you need to pick up the solution, whatever you are looking for. Then you will get a multiple number of solutions as a final outcome, not any single solution. Okay. Now, overall, so once we say that optimization, so normally we say it is the process of making something better. Obviously, we want to minimize or we want to maximize something, so we want to find out the better kind of results. And in this process, since normally optimization techniques we use to solve huge complex problems, high dimensional problems, then what we will get actually in the process, whatever the solutions you will get, those solutions may not give you the exact or the best solution. Rather, using optimization technique, whatever the solution you will get, those solution, it will give you the better solution. What is the difference between better and best? So I should say that better solutions resides in a very closer region to the best solution. Just quickly on. Yeah. So better solution will be there in a region which are very much closer to the best solution. So for this purpose, I need to tell you one concept. So let us check. This is our search space. The term I am writing, this is a search space. What is search space? What is search space? So in the search space, so a number of feasible solutions will be there. So whatever now I am writing a small circle. So let us assume, so all these are feasible solutions. Okay. What will be your target? So from this set of feasible solutions, you need to find out, okay, that which is the desirable solutions using your optimization technique. So number of solutions. So maybe out of these solutions, one solution is that your desirable solution, which is better you are looking for. So that you will get by applying the optimization techniques from the set of solutions which are there in this particular search space. Okay. Now let me come to this one important. Yeah. So again, one important kind of things are there that once that we are starting with our optimization techniques, then we may start with a single solution as well as we may start with a set of solutions. So as I mentioned, so these are our feasible solutions. So once you will start your optimization techniques, maybe you will start with a single solution. So if you start your optimization process with a single solution, then what should be your objective? Your objective will be to iteratively update the solution quality. Now, how to update the solution quality? So to update the solution quality, what you need to do? So to update the solution quality, so you need to change these parameters. Just one. Hello? Yes. Good morning. Yes, tell me. Call me after 5 o'clock. ठीक है 5 o'clock के बाद कॉल कीजिए. ठीक है. So yes. So what I was telling, so okay, so this may be the search space and number of feasible solutions are there. Okay, so you may start with a single solution. Your optimization technique may be started with a single solution. Then what you should do? What you are looking for? You are looking for the best solution in that particular search space. Okay, so if not the best solution, then you are looking for which is the better solution. That means which is closer to the best solution in this search space. So you may start with a single solution. Then you need to iteratively update this solution quality. How to update the solution quality? So to update the solution quality, you need to change the parameter values of this particular solution. So once what are the parameters for traveling salesman problem? So since we discussed already the fundamental ideas behind traveling salesman problem, the cities are the parameters in the traveling salesman problem. You can change the sequence of the cities. See, so if you change the sequence of the cities, then obviously whatever your optimization process or whatever the objectives you are looking for, the objective function value will be changed. So cities are the parameters for your traveling salesman problem. So if you want to update, that means update your solution. That means you need to change the sequence of the cities in your problem. So like that here I am telling. So to update this particular solution, you need to change the parameters of that particular solution. Okay, so if you change, maybe it will lead to this. Okay. Again, if you show fast iterations, you have changed this. It is moving to this. Again, you are changing. Then this will lead to this one. Again, you are changing. Are you getting how we are exploring the various solutions in the search space by changing the problem parameters or the solution parameters? So if you continually do that, obviously at one time, you will reach to your desired solutions. Now again, so here a critical questions may come. So I'm telling something regarding solution quality. So how to find out what will be your solution quality? So for that purpose, to find the solution quality, you need to use the objective function or the fitness function concept. Now another question, sir, how to compute the fitness function? If I say the problem of traveling salesman, so TSP, then how to compute the fitness function? Let us say this is our TSP problem. Let us say it is very simple TSP problem. Okay, this is your starting city where we have started visiting the city. And suppose this is the cost of the city. This is cost C1, this is cost C2, this is cost C3, okay, cost C4. So what will be if our objective is cost minimization, then what is the fitness function here? So here fitness function, it will take the summation of all the cost. In the which route the salesperson is traveling, so what are the costs associated in that rule? Simply it will take the summation of all the cost. So that will be your fitness function for your traveling salesman problem, if you are working with the cost. So based on the problem, you need to decide that what will be your fitness function. Okay, so if I tell you another problem, suppose we are taking a string. Okay, so suppose this is a binary string. Like that, we are taking a string. Okay, so this is a string. Binary string consists of 0 and 1. If our objective is to find out in which string maximum number of ones are there, max one problem, this problem is known as. This problem again I will discuss today. So if our objective is that in this string, okay, that we want to find out the string where maximum number of ones will be there, then what will be the fitness function here? So then your fitness function, it will calculate what are the number of ones. Simply like that, na? Fitness, so I am telling the term, that is fitness function. Fitness function. So what fitness function will do? So fitness function will do, suppose x with the s with the string, so f of s, so here 1, 2, 3, 4, 5, 6, it will be 6. Are you getting? If our objective is to find out the maximum number of ones in a particular string, then your fitness function simply it will count how many number of ones are there in that particular string. So this is the fitness function. That means fitness function will determine the solution quality. If you are working with maximization problem, then what will happen? More with the value of fitness function, more will be the solution quality. If you are working with a minimization function, then what you will do? What will happen? The less with the value, more will be the solution quality. You're getting the fact. So fitness function, so it is used to determine the quality of a solution. Okay. Or sometimes we can tell this is a fitness function, or we can tell this is an objective function also. So now the point we are trying to convey. So we started with a single point search algorithm, single point based. That means we are starting with a single solution. Slowly we are proceeding towards by iteratively changes the solution parameters. Okay. Now, second one is this population-based search algorithm. Here, what we will do? Population-based search algorithm. Again, I will draw the search space. Population-based. That means here, instead of starting with a single solution, you will start with a pool of solutions. Let us assume. So I am starting with this pool of solutions. Try to find out the fact behind this. Population-based. So instead of starting with a single solution, you will start with a pool of solutions. Now you may ask me, sir, how you will select the pool of solutions? My suggestion is that the pool of solutions need to be generated randomly. One important observation behind these optimization techniques are there. Optimization techniques are incorporating the concept of probabilistic randomness in all of the optimization techniques. Okay, we are in simply the stochastic nature we are incorporating actually to generate the randomness. Now again, some question will be there, sir, what is the why randomness is required in your optimization techniques? If you don't use randomness, then what will happen? Okay, that point I will answer. But here, what I mean to say that population-based search algorithms, you need to start with a pool of solutions, not a single solution. Then what will happen? Let us assume here we are starting with 1, this is 1, 2, 3, 4, 5, 6. We are starting with a 6 solutions. Then what we will do? So initially you need to find out what is the average fitness value. Initially you need to create randomly this 6 set of solutions. Then what you need to do? You need to find out fitness value for each and every individual solutions, and then you need to find out the average fitness value of those solutions. Then what should be your objective here? Same objective. Earlier, we started with the single solutions. We are randomly or iteratively updating the solution parameters. Here also, we are starting with a pool of solutions, and our objective will be, okay, we will nurture this set of solutions. Okay, whatever solutions we are starting, 6 solutions, we will nurture, we will do some things, okay, on this set of solutions, so that in the next iteration or next generation, average fitness value should be improved. See the situation. I am telling that in the next generation, we will do some kind of concept, some kind of ideas, some kind of exploration, or some kind of mechanism we will do on this set of 6 solutions, so that in the next generation, average solution quality will be improved. So you're getting, so average solution quality improving means what? At least some of the solutions are improving now. Fitness value of some of the solutions are improving. That's why average fitness value is getting improved. Again, the same thing here also. We will change the parameter values, the parameter sequence of parameters, or those parameters of those solutions. but in a different manner. Okay, here normally we will apply two concepts actually. So that is reproduction. So basically three things. So first one is selection, second one is crossover, third one is mutation. This crossover and mutation are normally said to be reproduction operators. So now see the fact. So we can start with a single solution. We can start with a multiple number of solutions also. But our objective is fixed here. Objective is that each and every iterations, if we start with a single solution, that solution quality should be improved. If we start with a multiple number of solutions, average fitness value of those set of solutions should be improved. How to improve it? How to improve the average fitness value? Okay, so that is our point of concern. So then we need to discuss how to improve that particular thing. Now, actually, so whatever things I am trying to convey, so actually optimization techniques. So two approaches are there to deal with these optimization techniques. One is the heuristic-based approach, and second one is the meta-heuristic-based approach. Now, some important differences are also there between heuristics and meta-heuristics. Optimization techniques we are discussing. So these are two approaches actually. Two process. One is heuristic approach, second one is meta-heuristic approach, okay, to deal with these optimization related problems. Now, this what I will say that this heuristic approach, let us start. Heuristic approach itself a very much innovative approach. Innovative approach means that is different from your traditional approaches. Okay, different from your traditional approaches. See. What the heuristic approaches will do? Heuristic approach reduce your mental effort to make the decisions, simplify the complex, difficult questions, fast and accurate way to arrive at a conclusion, help with problem solving. So this is little bit different, innovative from your classical or your traditional approaches. Okay, but again, once we will see that meta-heuristics, meta-heuristics are most powerful than the heuristic approaches. In the meta-heuristic approaches only, we are applying the concept of randomness. The concept of randomness are not there in the heuristic approaches. Concept of randomness we are being applied in this meta-heuristic approach. Heuristic approaches are deterministic, but again, believe me, you can apply heuristic approaches also to solve a number of problems. So, if you belongs to computer science, maybe some sorting, searching problem. So this sorting, searching problems belongs to heuristics. So these things are problem dependent. On which problem, which heuristics you need to apply. But if I say regarding meta-heuristics, which actually application area or applicability is much more wider than the heuristics. It is problem independent, meta-heuristics. That means simply if you use meta-heuristic approach, the problem you need to map with those approaches and go on proceeding to solve that particular problem. Again, the main crucial point I need to highlight that meta-heuristic approaches, two things will be there. Main crucial point, that is randomization plus heuristic. If you search in Google, what is meta-heuristic? Perhaps it will show you it is a heuristics of heuristics. Better I should say, meta-heuristic means randomization plus your innovative ideas, which is different from your classical ideas. Okay, as well as I should say, meta-heuristics approaches are nature-inspired. But both heuristics and meta-heuristics, that will give you that this nature of solution inexacts, which are near to the optimal one. That means both of these things it may give you the solution which is closer to the best one or better solutions. Now, you may ask me one important observation, sir, why this randomization is required in these meta-heuristics? Why these nature-inspired concepts are required in these meta-heuristics? If you don't use this concept of randomization or meta-heuristics, then what might happen for these meta-heuristics? So for this purpose, I need to tell you this concept. So once we are solving some problem, there may be two kinds of solution. One is local optimum solution and second one is global. What is local optimacy? We are solving some problems, okay. So let us see. We have started from here on. We are trying to solve the problem. So here, local optima means locally it is better. Okay, see, from this point, if we move this side or this side, so your solution quality is falling down. Fitness value. So this is the fitness, this way the fitness value is improving. So if you are moving in this manner, so if you are moving in this manner right now where I am pointing, okay, so at this particular point, what you will feel? At this particular point, the fitness will be better from its nearby or this neighbor solutions. This point fitness will be better from these nearby solutions. So what will be your misconception here? You may be confused. Okay, you may feel okay. That means from this point, if I move to the nearby solutions, my solution quality is degrading. That means maybe I have reached to my desired solutions. Because you have some problem. Okay, you are trying to solve the problem. You don't know now which is your optimal one. Because in a short space, number of solutions, infinite number of solutions will be there. Then at some moment, you will get some solutions. And you will find out, okay, that means if you are moving to the nearby solutions are not good. That means you may feel, okay, let me stop my process. I have got the targeted solutions. Is it like that? So this is locally based solutions. That means in this surrounding, this is the best one. But again, if you move further, then you will find out another best one is here in this particular point. Now see the situation. Now if you are in this point, if you moving nearby areas, you are finding solution qualities you are not getting good. So you are restricting yourself in this point only. Then my question is, how to come out from this kind of situations? Simple fact is that you may start with this. Then once you are moving from this solution to the nearby solutions, although fitness value may be less, but again you have to move. So is it like that? See, try to understand. So once you are moving from one solution to the second solution, always you will expect improvement. But sometimes if there is an improvement, then again you should move. Like our life only. Okay, full of failures and a random success are there, very few. So if we suppose right now I am in some point, okay, I am finding, okay, so that if I am moving a little bit here, there, I am finding that I am not getting any good objectives. So should I fix to my position or I will try to improve myself? If I little bit move, maybe a little bit fall down, but again, I maybe again failed. But should I stop my career objectives if I fail again? Okay, so considering the failure that sometimes you should move although you have got the failure, because again the failure may lead to some success. So this is the idea actually. Sometimes you may get, once you are moving from this solution, you are moving from this is better solutions, okay, to other solutions, you are finding you are not getting in a good solution. But again you have to move. But is it like that all times you will move? No. Once you are in a better position, then based on some probability, all time you should not move. Because sometimes, again, you need to move so that you can get a good solutions in the longer run. If I stop at this point, then I may not get to the global optimum solution at any point of time. So, but if I take some risk, okay, I am getting some bad solution. Again, I am moving. See, this is based on randomization only. Always I will not move to the poor solution. Let us say technically, one is good solution, second one is poor solution. Always I will not move to the poor solution. But stochastically, based on some probabilistic value, I will move to the poor solution also, so that in the longer run, I can get a good solution. So for that purpose, randomness is required. So to come out from the biasness, moving here, again at the same point we are getting the same situation. So sometimes we need to adapt the poor solution also, so that in the longer run we will get the better solution. So this is the concept of local optima. Local optimum is locally based, global optimum means it is overall based. So our target is to reach to the global optimum only, not to the local optimum. That means once you are changing, let us come technically. So once you are changing the solution parameters, sometimes you will feel by changing those parameters values, you are moving to the your in the next iteration your solution quality is becoming poor. But again, sometimes, not always, based on the probability value, sometimes you need to adapt to the poor solution also. Because if there are any global based solutions, then you may proceed to the global based solutions by adapting the poor solution, sometimes based on the probabilistic value. So that was some ideas behind that, whatever I was trying to convey behind here is why this meta heuristics is, I am telling randomization plus heuristics. Again, some ideas is there behind randomization that obviously I will convey. Now, again, two key concepts that whatever I observed actually. So in this meta heuristics algorithms, one is exploration, second one is exploitation. Very important, crucial concept. What about the heuristics or meta heuristics or optimization techniques you will learn or your understanding? If you understand this two crucial concept, then maybe you will get your solution much more faster than. So what is exploration and what is exploitation? Exploration means diversification. Exploitation means intensification. So suppose you are moving in a search space where number of solutions are there. So initially, what should be your target? To explore the search space as much as possible. So in your search space, a number of solutions are there. So what should be your initial objective? Initial objective should be to explore the search space as maximum as possible. Now suppose after few steps, after few iterations or generations, okay, so maybe you are near to this solution and you are finding, okay, then this is relatively much more better solution. Then what you should do? Then slowly you should stop your exploration. You should focus on intensification. Intensification means what? So since this solution is good, so maybe which are the nearby solutions of this good solution that may be much more better. This is simply, the idea is like that. Normally we say recent past is a good indicator of near future. That means once you are getting some good solution, so that we may focus, okay, nearby solutions will be good. So if once you are getting some good solutions, again you are moving, again you are exploring, then what will happen? You lose, you will be too much distance from the good solution. Try to get the point. So initially you need to focus on the exploration. Slowly, once you are getting some good solutions, you should reduce your exploration and you should intensify your exploitation. With exploitation, what it will do? It will restrict you to move to search nearby areas of a good solution. So each and every meta-heuristics technique should be well balanced by this exploration and this exploitation. What about the optimization techniques you will study, you will find out that maybe most of the optimization techniques are not using any proper balancing mechanism. But if somehow proper balancing mechanism is applied, then you will converge much more faster manner. So that is one of my observations what I was trying to convey. Exploration and exploitation. This is very normal. Now, from our common sense also we can feel the situation. Initially we should explore as much as possible. But once you are reaching to some good quality solution, then you should restrict your exploration. You should focus on the exploitation part. Okay. Now, slowly, let me come to one example and one specific meta-heuristic approach. Then I will tell you that how to solve some problem numerically, but using that approach. Okay. So today, the thing I will show you that is genetic algorithm only, and I will show you that how you can use genetic algorithm to solve some numerical problems and what are the applicability of that particular thing. So, this genetic algorithm is population-based search technique. Already you know what is population-based search technique. You start with a pool of solutions and then you need to move. Now, the situation is like that. So, if you start with a pool of solutions, then what you do? I am starting with a pool of solutions. Okay. So, this is the pool of solution I am starting. Pool of solutions, this is a set of solutions are there. From the set of solution, I am selecting a pool of solutions. Let us say this is my pool of solutions. So how I should proceed so that my average fitness value will be improved in the next generation. So once I am selecting some pool of solutions, so each and every solution will have their fitness value. Then if I implement natural selection here, then now how to implement natural selection? My target is that once you are getting a pool of solution, on those pool of solution, I will implement natural selection. What is natural selection? Natural selection, the idea, okay, simply we are taking from our surroundings. So if you look carefully to your surroundings, you will get those who are adaptive to the changes in nature, they will survive, remaining will vanish. This is coming from the Darwin's theory of survival for the fittest. Those who are adaptive to the changes in nature, they will survive, remaining ones will slowly vanish. So this natural selection. So exactly this concept we will be utilizing in our set of solutions, in our pool of solutions, which we have randomly generated at the starting of our genetic algorithm. Now, one more important concept I want to tell behind what is my observation behind this natural selection. So can I tell, once you are applying natural selection, can I tell that, okay, you are applying natural selection, that means technically if we say, which solutions are good quality solutions, they will survive in more number. Which solutions are poor quality solutions, that will vanish. Naturally, if you look closely, carefully, you will get the concept like that. Those who are adaptable to the changes in nature, survival probability for them is more. But those who are not adaptive to the changes in nature, survival probability for them are less. But should I say survival probability for them are zero? Actually, those who are not adaptive to the changes in nature, some of them are also surviving because of the luck factor. There's a natural selection only. We have no control on that part. If you look closely, you will get the idea. If you are not getting the point, let me take one example. Giraffes. So initially, giraffe with short neck, giraffe with long neck, both kind of giraffes were there. But slowly, giraffe with shorter neck became in less number. Giraffes with long neck or hard neck, we can find anywhere, at many places. How these things are become? Why giraffes with shorter neck are surviving in more number, and giraffes with long neck are surviving in more number. Giraffes with short neck is surviving in less number. Can I say survival probability of giraffe with short neck is zero? Some of the giraffes who are short necks, again they will survive, by the chances of luck factor. Natural selection only, non-zero probability. So this is the crucial concept behind any meta-heuristics algorithm, behind the natural selection. You see, we are trying to implement the concept of natural selection in this genetic algorithm. So what kind of conclusion we can take? Okay, which solutions are better solutions? We will select them in more number, we will transfer to the next generation. But which solutions are poor quality solution? Idea is that, again, some of the solution will be selected, will be shifted to the next iteration or next generation. Why? Because, as I was telling, they may survive due to luck factor. You're getting the fact. Once I'll show the example, then the things will be much more clear. So once you are moving from one generation to second generation, solutions which are having good fitness value will select, they will be moving in more number, higher chances being selected for those solutions. But those solutions, fitness value is less chances of selecting those solutions. But at the same time, I must tell that poor quality solution have a non-zero probability to be selected, while probability is less. So what is my conclusion? So more number of good quality solution will be selected and less number of poor quality solution will be selected. Okay. So up to this point, now it is fine. So now the main natural, this is the main concept. One is the natural selection. Second one is that genetic inheritance behind this genetic algorithm. What is genetic inheritance? Genetic inheritance, it is telling if parents are better, their offsprings are supposed to be better. Here, what is our concept? So, once natural selection has been done, what is there in your pool of solutions? Once natural selection is over, then in your pool of solutions, number of solutions will be always fixed. You cannot change it. Let us assume initially number of solutions were 6. So once you have implemented natural selection, what you have with you? More number of good quality solution, less number of poor quality solution. So average fitness value will be automatically improved since we have more number of good quality solution. Then here what will happen? So now if you randomly select 2 chromosomes and if you apply some reproduction process on those pair of chromosomes, then what about the offspring you get? Or this mating process on those 2 chromosomes? Those offsprings are supposed to be better. See, after natural selection, what you are doing? You are randomly selecting 2 chromosomes. Now, since after natural selection, in our pool of solution, more number of better quality solutions will be there. So if you select 2 chromosomes randomly, see, I am uttering the term random, not doing any biasness. That's why meta-heuristics concept, I told initially, is all randomized concept. Randomization plus heuristic, that is known as meta-heuristic. Since more number of better quality solutions were there, so if I select randomly 2, automatically, so probably the chances will be more that 2 good solutions will be selected for the mating process. And then apply mating process, that is called crossover technically. Then what will happen? Genetic inheritance it is applying. If parent solutions are better, child solutions are supposed to be better. Then what is happening? Then from those 2 parent solutions, whatever the child solution will get, their fitness values is expected to be much more better. You're getting the fact. So this is the idea actually that we are going for this natural selection. Then from this natural selection, what we are going? So from this natural selection, we are trying to find out, okay, that randomly selecting not only 2, we are randomly selecting a couple of chromosomes, few pair of chromosomes. How many pair of chromosomes? I should not tell that term chromosome. Actually, in genetic algorithm, each and every individual solution is known as chromosome. Since we are applying the genetic term, so we are telling each and every individual solutions are known as chromosome. And a chromosome consists of a number of parameters, and the parameters are called genes. If we say in traveling salesman problem, so our sequence of cities are a chromosome, then obviously each and every city will belong to some gene, because a chromosome consists of some gene only. Okay. Now let me focus on let me focus on these ideas. That what I was telling initially, that from this natural selection, what you are getting. So from the natural selections, we got some pair of good solutions, and then by applying the then on those pair of good solutions, we are applying this crossover. Crossover means, I mean to say, some reproduction operator we are applying. Then what we are getting as a result? As a result, we are getting from a set of 2 solutions, we are getting 2 better quality solutions. But I should say exceptions also will be there. since all these things are getting done randomly. So exceptions is very normal here. Okay. So now see. So after crossover, what is happening? So after crossover, again in our pool of solution, if we find the average fitness value, you will get average fitness value also will be. Because after natural selection, we got good solution, average fitness value improved. From those natural selections, we selected randomly two solutions and we implemented the reproduction kind of things. And as a result, from two solutions, we are getting two good solutions. Our number of solutions will fixed 6 only. It will not change. But again, your average fitness value will be improving. Not always, but probability is telling that it will be improving actually. Okay. Now let us see the situation actually, how things are happening. See, so this is the flowchart for our genetic algorithm. So initially, so we will create, as I said, population of chromosome. As you know, chromosome means these are our solution only. Each and every candidate solution we are telling as a chromosome. Then we need to determine fitness value of each and every chromosome. Quality of the solution it will result. And then we need to go for selection, natural selection. What it will do? Natural selection means it will select automatically which solutions are better solution, they will be selected in more number. Which solutions are poor solutions, so they will be selected in less number. Okay. That means in our pool of solution, more number of better quality solution will be there. Then you need to perform this crossover and mutation. Crossover. I will tell. Already I was trying to convey the concept of reproduction matching process. That is crossover. So after crossover, you need to perform mutation. What is mutation? Mutation means that is random changes in gene. If you do, suppose you are working with this traveling salesman problem. If you randomly changes some cities, then maybe your solution will be highly improved. Sometimes it will be degraded also, both chances are there. Okay, so crossover means random changes in gene. In the expectation is that if we do some random changes in the problem parameters, maybe our solution quality will be improved. So then after performing mutation, again you will be in the same loop. Again, you will be coming to here. Again, you need to determine the fitness value of each and every individual. Maybe you are confused, Sai, why you are computing fitness value each time? Because after crossover and mutation, our problem, the solution is getting changed. Solution is not the same which was earlier. After applying crossover and mutation, our solution is getting changed. If you look, traveling salesman problem, the arrangement or sequences of those cities are getting changed. Then obviously, again, we need to compute the fitness value. In each and every generation, we need to compute them. So that's why so here time compression is sometimes very much higher. Because each and every time we need to compute the fitness value. And if your fitness function is not easier, then unnecessarily it will consuming more time. Okay, now let me, in brief, let me tell you the facts. So I told you many things. So now how to encode the chromosome, how to implement the crossover, how to implement the mutation. What are the issues are there within these things? So crossover, very simple I told that crossover means, not crossover, that chromosome. So for each and every problem, you should represent the problem using some encoding technique, chromosome. So how to encode each and every solution for each and every problem, so that you can do all this crossover mutation and all other operations. So let me see how to encode this chromosome or what is encoding technique. You can represent a chromosome using binary representation technique. You can encode your problem using this binary 0 and 1 values. For each and every problem, you cannot encode it, at least. Now, for certain kind of problems are there, where values of each and every parameter are yes or no, binary values, two values, positive, negative, true, false. For those kind of problem only, you can use this binary encoding technique. All concepts theoretically I told, but how to implement in the computational space? To implement in the computational space, you need to encode that whatever your problems in a proper encoding technique to get the chromosome. What I told, initially we should need a pool of solutions. Here, each and every solutions I am telling as a chromosome. Now, what will be the chromosome? How to represent a chromosome? So to represent a chromosome, so we need to use some kind of encoding technique. One of the encoding technique is called binary encoding technique. So in binary encoding technique, as I was telling, that we are representing the problem parameters, values of the problem parameters using zeros and ones. It is not possible to represent each and every problem using this binary encoding technique, as I mentioned earlier. For a few problems only we can represent. So number of techniques are there actually. So as I mentioned, so binary encoding technique may be fruitful only for those problems where for each and every problem parameter, there may be of two values, either 0 or 1. If you know the knapsack problem, the knapsack problem, by the better I should say 0-1 knapsack problem. So that can be represented using this binary encoding technique. You need a set of solutions to start with your genetic algorithm or any population-based meta-heuristics optimization techniques. So how to represent the chromosome? That is our now concern. That is that point only we are concerned. Very typical actually. To encode your solution in a proper format, or to encode your chromosome in a proper format. Based on this only, your entire genetic algorithm is depending how you are encoding it. And as I told, this is one of the most difficult tasks behind genetic algorithm. Binary encoding technique is easier to understand, easier to learn, but it is not applicable to many problems. It is applicable only to a few problems, like this 0-1 knapsack problem. So let me discuss what is this 0-1 knapsack problem. In this 0-1 knapsack problem, you have a knapsack with you. You have a bag with you. You have some items. Each and every item have some values as well as having some associated weight with that. You have a knapsack, that means a container or a bag. You have a set of items. Each and every item has their associated values, having their associated weight. What is your objective? To put the items in the bag so that value will be maximum, but knapsack capacity you need to maintain. Otherwise, the bag will be damaged. See, you need to put the items in a bag in such a manner so that your value, because each and every item associated with some value, and value means I need to tell the fitness value. Value will be maximum, but you need to maintain the knapsack capacity. Otherwise, the bag may be damaged. And here, interesting thing is that you cannot break any item. That's why 0-1. Either you can put the entire item in the bag, or you should not break it. You cannot break it. So what is the situation here? So once you have some set of items, see, item you can put in the bag, you may not put in the bag. So two values. An item you may put in the bag, cannot put in the bag. That means for each and every item, only two values, yes or no. So that's why I told, or when for each and every things item, only two values will be there. Item means here I mean to say problem parameters. Two values will be there. Then those problems are well suitable to represent using this binary encoding technique. So this is a knapsack. This is knapsack problem, very well known 0-1 knapsack problem. Whatever I mentioned here, the same it is written in some numerical example. Now again, you know that now if you work with this traveling salesman problem, so a traveling salesman problem, you know, it is a different problem. So then your binary encoding technique will not work for your traveling salesman problem. Then what will work? Because you have a number of cities now in your hand, and you cannot repeat each and one city 2 or 3 times. Very complex problems actually. Then how to represent? To represent this the TSP kind of problems, we use this concept that is called primary, that is called permutation representation. Permutation representation. Now, what is permutation representation actually? See, solution is represented by an order of elements, see, where none of the elements are getting repeated. If you find some problem, while solution will be represented by order of elements, where none of the elements will be repeated. Here, TSP1 solution, you tell me, what is one solution? Sequence of cities now. Starting city, visit the city at most one time, come back to initial city. So it is a sequence of cities, where none of the cities are getting repeated except the initial city. So obviously, for this kind of problem, we can use this permutation representation. See, here these are the cities, 1, 5, 9. So you can you tell me any cities are repeated here? None of the cities are getting repeated here. If cities are repeated, that is not a TSP problem now. Okay. Now another thing is there that so once you have encoded your problem, you know that problem encoding is done. It may be a binary encoding technique, it may be permutation encoding technique, it may be any other encoding technique. So once encoding technique is done, then you need to go for finding the fitness value. Okay, once fitness value is computed, then you will go for selection. Because as you can remember, I told, once you have a pool of solution in your hand, then you need to apply natural selection. What natural selection is going to give you? That means which are better solution that will be selected in more number, which are poor solution that will be selected in less number. At the same time, number of solution in that pool of solution will be fixed. If it is 6 before selection, after selection also it will be 6 only. It will not be changed. But more number of good solution will come, less number of good solution will come. Now you may feel, sir, you are telling that fact very easily. So how technically to represent that? Yes. So technically you can represent using 3 ways. One, you know, this is not 3 ways, multiple number of things are there. Here I have mentioned 3. Proportional, WT, tournament. Now let me check how tournament selection is getting done. This is very interesting. How WT wheel selection is getting done. See, here what we are doing. So let us here we are taking 3 solutions. Okay, ABC. And they have the fitness value of 3 solutions, 3, 1, and 2. Now, if you assign these solutions in the wheel based on their probabilities, then what will be the probability of allocation for solution A? Probability is 3, summation is 6, so 3 by 6. So that means 50%. So 50% of the wheel will be allocated by solution A. 17% will be allocated by solution B. 33% will be allocated by solution C. Now let us say you are taking some point here, fixing some point. Okay, and you are spinning the wheel, let us say 5 times. You are spinning the wheel 5 times. Now can you tell which solution will be coming in, selecting in more number in this particular point? Or which one will be selected in less number in this particular point? If we say spin the wheel, obviously which solutions are good solutions, they have a higher chances to be selected here. But can I say poor solution have a 0 chances to be selected? No. Poor solutions also will be selected, but in less number. See how using this rowdy wheel selection we are implementing this natural selection. So simply another important is that tournament selection. Here also the same concept. Okay, that means if we apply tournament selection, again the same thing will be there. What is tournament selection? K-way tournament selection, you know. We select K individuals from the population randomly. and then select best among them. KY tournament. So if K equal to 3, then what we will do? Check here K equal to 3. So randomly we have selected 3 solutions, randomly. And then check which is best among them. So here fitness was 5. So here fitness was 5, 2, 2. See, here 5, 2, 2. Which was best? Then A is best. So L is selected. So initially we were selecting randomly 3 or K number of solutions and then going to find the best among them. Here also the same thing. Which solutions are better? They will be selected in more number. Which solutions are poor? They will be selected in less number. The same concept. Since all the getting done randomly, we have no concept on, we have no control on that part. So let us assume that is being done. Okay, that is being done. Selection is over. Then it is about crossover. What I told you can remember. After selection, we'll go for crossover. Crossover, what it will do? So from after selection, it will select randomly couple of solutions and it will do some process on those couple of solutions. How the process technically can be implemented? So crossover means partial exchange of information between two randomly selected parent chromosomes. Since it is an exchange of information, if you check this, it will be very clear. This is called single point crossover. So this is one parent, this is second point. I am telling this is my crossover site, crossover point. Check it, what is happening. Exchanging of information, just check. So after crossover site, so it is coming from the second, and here it is coming from the first. Are you getting? So after crossover between, if we apply crossover between a set of two solutions, we will get a two child solutions or offspring solutions. Here, what is our objective, as I mentioned earlier? So genetically, we feel that if parent solutions are better, then if we apply crossover, then objectives of then offsprings or child solutions also is supposed to be better, not always. But probabilistically, we can tell that. So this is the idea that how we'll apply crossover. Now I will show you more clear picture. Now, if you are using binary encoding technique, then in this manner you can apply crossover. See, these two are chromosomes, okay? So this is our crossover site. You know, a number of different types of chromosomes are there. Different types of crossovers are there. But for the sake of simplicity, to tell the idea most significantly, so I am applying this only. So crossover. These two binary encoded chromosomes we have selected. And randomly, you may ask me, sir, how you are selecting the crossover site or crossover point? My answer is randomly you are selecting that. We have no biasness. Sir, how you are selecting the chromosomes to be selected for crossover? Again, my answer is that after natural selection, I have no control. Randomly you are selecting on. So this two chromosomes selected. This is crossover point. Now see, up to this it is okay, but see, second part, it is information exchange. See, this is coming here, okay, second, and this is here. So simply this is exchange of information actually. So by which we implement this crossover. But you know, it is exchange of information only, but you know, how to implement the crossover. So that will depend purely on your encoding technique. What encoding technique you are using? Okay, what problem you are solving? Based on that, you need to fix your crossover technique. Many kind of crossover techniques are there. Okay, I will show you one most important crossover technique. Once I will solve, I'll give you some idea behind this traveling salesman problem. Now this is a mutation. What is mutation? As I mentioned earlier, mutation means random changes in gene. Now, which solution you will select for mutation? Again, it will be done randomly. Which gene you want to select for change? Again, these things you need to do it randomly. We have no control on that one. Okay, let us assume, okay, so this chromosome offspring you are selecting after that crossover. Randomly, I have no control that I am repeatedly I am telling. Randomly, I am selecting, let us assume this gene. then that means this one will become 0 here. But not only one gene, you can select multiple number of gene also for mutation. Getting? So here you are selecting two genes. Just check. Second problem. This one and this one. So this is becoming 1, this one becoming 0. Okay. Now this is another kind of mutation, swap or scramble mutation. So many kind of mutations are there. Okay. So now see, what is swap mutation? See, we select two positions on the chromosome, interchange their values. So these two positions are selected and we are interchanging their values. 6 and 2. Now, can you tell me, will it be perfectly fitted for your traveling salesman problem? Yes, that can be perfectly fitted. Because traveling salesman problem, we need to take care that cities should not be repeated. That you need to take care. That means in a particular chromosome, there should be no repetition of the cities. Whatever scheme you are using, but you need to take care. What is scramble mutation? And again, interesting thing. So we are selecting a subset. Then what we are doing? Randomly changing their positions. So that also can be applied for this traveling salesman problem. Okay, now let us discuss the max1 problem. What is this max1 problem and how to solve using this genetic algorithm? So what I told initially, what is your objective behind this max1 problem? So max1. So suppose we want to maximize the number of ones in a string of binary digits, as I mentioned earlier. So you have a string of binary digits. That means you have a string of zeros and ones. So what is your objective? Your objective is to maximize the number of ones. You may feel, sir, it is too much easy. Why you are applying genetic algorithm to do that? Yes, no, we are applying genetic algorithms to feel that, okay, how the genetic algorithm is working according to our knowledge. Okay. So obviously, so here we can encode now this max1 problem. Obviously, we can encode using this binary encoding technique. So here, what is an individual? Individual means on chromosome. Okay, so it is a binary digits. It has a string of binary digits. Now, what is the fitness value? Obviously, as I mentioned earlier, fitness value for the max1 problem is the number of ones in its genetic code. So this may be a string or a solution for max1 problem. Now you may ask me, sir, how many number of 0 and 1s you are taking? Actually, this is based on the problem parameters. In traveling salesman problem, how many cities are there? Based on that, you need to select the chromosome size. Like in max1 problem, how many 0, 1 you want to consider? It will be based on that. Okay. Simply, I should say that what are the number of parameters? That number of 0, 1 you need to take. Okay. So we start, now see that here what we are doing. So we are starting with a population of n random strings. And suppose L is 10, N is 6. L means what? L string of L binary digits. N means what? So L means a size of that chromosome. That means total number of ones and 0 are 10. Size of the chromosome. What is N? What are the number of solutions you are using in a population? That is 6. Now you may ask me, sir, how to determine that how many solutions we keep in a population? That is obviously for the simplest problem we are taking a 6. But once you are working, it may be we are taking 50, 100 number of solutions in a population. Okay. Now see. Now, so what is your initial task now? Now our next task is to generate the initial pool of solutions. See, this is a population-based algorithm. So we are generating the initial pool of solution. So randomly you are generating the initial pool of solution. Just check. So initial pool of solution I have generated. And how many solutions are there? You will find out 6 solutions are there. As I mentioned earlier now, that number of solutions in your population is 6. Okay. Now check how many 0 ones we are taking, just check. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Already it was given. So that chromosome size is 10. A number of solution in the population is 10, is 6. Make it clear. Population chromosome size is 10, but population size is 6. Population size means how many number of chromosome will be there. Chromosome size means how many number of gene will be there. Gene means the problem parameter. Okay. So what will be the fitness value for this string? FS1 means we are finding the fitness value for this string 1. It is 7. How many ones are there? 1, 2, 3, 4, 5, 6, 7. Since 7 ones are there, that's why you are telling your fitness value is 7. So here, into how many ones are there? This 1, 2, 3, 4, 5. 5 ones are there. So we are thinking, we are considering this is 5. Okay. So based on that, we are finding the fitness value, okay, of this initial population. How many number of ones are there in each and every solution or chromosome? Based on that, we are finding it. Now, what is the total fitness value here? So total fitness value is 34. If you take a summation of all these things, you will find out total fitness value. Now, what is the average fitness value here? The average value will be obviously 34 by 6, that is 5.6. Okay, so see. So what we did initially, see, this is our, here we are simply formulating what is our initial population. So that we have formulated the initial population. Next will be, what we will do next? What will be our next objective? To go for natural selection. What natural selection we will do? It will consider good solution in more number, poor solution in less number. But at the same time, number of solution in the population will be fixed. But right now, what is the number of solution in our population? 6. Okay, this 6. So it will be 6 only after implementing the natural selection. Now see. So this Rowley-Tevil selection mechanism here you are using for this natural selection. As you know, Rowley-Tevil already you have seen. A Rowley-Tevil outer tendency is like that. Which are the better solution? That will be selected in more number, poor solution selected in less number. Our probability of selection is less. So that only the same thing, you know, that we have applied in this Rowley-Tevil selection, you know. Okay. So now if you do that, then what will happen? So after implementing this, you know, natural selection, what you will get? Just check it, what we are getting. You are getting solution S1, S2, S3, S4, S5, and S6. So which solutions are missing? Because 6 solutions are there. Which solutions are missing? See, S1 we are taking, S3 we are taking, S5 we are taking in 2 numbers. As I told, better quality solution will be copied in more number. Poor quality solution will be copied in less number. So solution 5 has been copied 2 numbers. Solution to 1, solution 3. What is? So where it is missing? Where is solution 6? Let us check. Solution 6 fitness value was little bit less. That's why. So that has been discarded. But again, solution 4, that is also less. But as I am telling you, each and everything you cannot discard. Some of the poor quality solution, again, by nature or by luck factor, they will be selected. They will be moving to the next generation by the natural concept or by the concept of this natural selection. Now see here. So solution 5 has been copied in 2 number. Solution 5, what is fitness value? Fitness value is 8, little bit more. As I told you now, that which solutions are better, they will be copied in more number. But here I am not sure that only 8 will be copied in more number. Any other better quality solution, 7, maybe 5, they may be also copied in more number. All things are getting done randomly, as you know, by the help of natural selection. Okay, so you have seen the probability wheel. Better solution will be selected in multiple numbers, but poor quality solution will be selected in less number. Okay, so that you are getting. That means our natural selection is done. So solution 6 is here missing, and solution 5 is copied in 2 number. Next, what is your objective? You will go for crossover. So next we'll go for crossover. So see, then crossover what we will do? So we have this pool of solution. Now crossover means we need to randomly select some pair of solutions. Now which pair of solution will be randomly selected? We have no control on that. Okay. So here simply the concept is like that. Whatever the solutions you are getting after natural selections, you can select randomly any two. But probability is telling that since after natural selection, okay, you are having more number of better quality solutions. So probability of having couple between two good quality solution is more. Probability of getting paired between two good quality solution is more, obviously. So this is very natural phenomena. So let us say randomly we are selecting 2. See. And one thing you need to know that crossover probability. One important concept is there that is called crossover probability. What is crossover probability? So crossover probability is telling that how many solutions from the crossover, from that pool of solution you will select for the crossover. Is it like that 100% solution you are going to select for crossover? Or you are going to select only 20%, 30%, 40% solution for crossover? So we should not select 100% solution for crossover. Normally crossover probability belongs to 0.6 to 0.8. That means maybe 60% or 80% solutions you can select for the crossover. Are you getting? So how many pair of solutions you will select? So that is depending on this crossover probability. Okay. And here what you are doing, just check. So let us assume these two solutions are selected randomly for this crossover probability. For this crossover, based on the crossover probability. And then here we are doing some separate crossover check. This we are selecting. Okay, subset of the string we are selecting. Okay. And then what you are doing? This only you are exchanging this. It is coming here and it is going here. This is not your single point crossover. This is a different crossover concept actually. As I told, many kind of crossover concepts are there. Whatever problem you are solving, based on that, you need to define what type of crossover you are going to apply in your process. So these 3 and these 3. So just interchange, you will get that. Okay, so you have implemented now crossover. Then what is your objective? See. So then your objective is that you will go for this mutation. Okay, now is it like that? Each and every string or each and every chromosome, whatever you're getting after crossover, you will apply mutation? No. Again, the concept is that some mutation probability is there. Mutation probability is defining how many chromosomes you will be applying the probability. How many chromosomes you will be applying mutation. Normally, mutation probability will keep between 0.2 to 0.4. Mutation probability is much more lower than this crossover probability. Because, once you are doing mutation, it is doing a huge shift from one solution to the second solution. So if you do mutation more, then what will happen? then you will lose your solution quality actually. So more normally, I can tell that mutation, you're applying the. Let me show you the one important idea behind that. Suppose these two solutions you are selecting, you are applying crossover. Then after applying crossover, what will happen? You will be in a very nearby regions, maybe in this region. After crossover, these two solutions will be created. Okay, this is your parent one, this is your parent two, this is your child one, child two, which will rely in a very closer region. But if you do the mutation, suppose here, okay, you are doing this solution, you are applying mutation. Then from this, it may be becoming here. Huge shift in the search space will be there once you are applying this mutation kind of concept. So number of mutation probability to open, we are keeping low. Anyway, now see here. So here we have applied this concept of mutations. So as I was telling, not all, okay, only randomly select few strings and apply the concept of mutations. Okay, here what is happening? So maybe here they have applied this here. So that means this is becoming 0. And maybe this one becoming 0. As well as few other places also it has been applied. See, how many genes you are applying under you are keeping under mutation? Again, you need to do it randomly. Okay, how many, what about the chromosomes you are applying for the mutation? All things will be getting done randomly here. So this 0 is also there. So this 0 is becoming 1 like that. Here. This one becoming 0 here. So that means, like this is the concept of this mutation. So randomly changing, since it is a binary encoding format, so 1 to 0, 0 to 1. But if it is a different encoding format, then your situation will be different. Now you check. So after computing the mutation and crossover, if you take the fitness value, if you calculate the fitness value of each and every chromosome, and then if you take the average, then you will find out your average fitness values are improving. Let us check. In the new pool of solutions, if you take the fitness values, it will be 37. Earlier it was 34. So average fitness value is improving or not? Yes. Average fitness value is continuously improving. So that was our target only now. So we need to follow this until unless termination criteria are met. What is termination criteria for this genetic algorithm? We can tell that, sir, we will fix a maximum number of iterations. After that, we will close. Correct only. But again, for normally which are used in a significant computation, no. In after some consecutive, under some successive generations, if you find out average fitness value is not significantly changing, then perhaps you will feel your solution has converged. What I am telling. Maybe after generation number 100, 101, 102, 103, you are finding there is no significant changes in the average fitness value. What does it mean? Already you are getting to your desired solution. Normally you say you have converged, your solution has converged. You got the desired solutions. In some consecutive generations, if you find average fitness values are not changing, that means you can terminate. So that is an important termination criteria that is normally used by the researchers once they are solving it. So I'll show you another one. Okay, that is here another numerical problem where how we are applying genetic algorithm to solve. Now see. Here what is our objective? This is where again we are doing in different manner. So max of x square over this region. So 0 to 31, 32 number of solutions are there, okay? So here what you want to find? So if we do max of x square, then which one will be selected? You want to find, this is your objective function, max of x square. Okay, so we want to apply this in this for this values 0, 1, dot, 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 2, 3, 4 up to 31. Now you can tell easily, sir, you do max of 31 square, it will be maximum. Okay, so this is your search space. In this search space, these many solutions are there. Okay, so here from this, we want to find out our desired one. Obviously, our desired one is 31. So I will see that how genetic algorithm is moving us to the close to 31. So now how here what we are using representation purpose, we are using binary representations. This is a binary digit, this is the decimal equivalent of this binary number. We are using random initialization, population size 4, probability Hill selection, 1-point crossover. See, we are taking population size 4. That means in one population, 4 solution will be there. So let us see. Now check. Randomly, we are selecting the initial population, and it is a binary encoding format. Now you may ask, sir, from where you are selecting it? You see, from where you are selecting this initial population. So what it is given? 0 to 31. These numbers are given. 0 to 32. So these are the decimal numbers. These decimal numbers are given to us. Okay. So whatever initial population we are creating, so decimal value is within this only, 0 to 31. Because this is our search space now. In the search space, in our problem, these things are there. Okay. That 0 to 31, these many values are there. We want to find out. Okay. So which will be satisfied by our objective function, which is max of x square. If we put max of x square values on this, what are the inputs we have given in the search space, 0 to 31, then where it will be maximum. Obviously, it will be maximum 31. So we'll see how we can get that. We're getting, so this is population size, you see. So we are initializing. So this is 0 to 31 values only. Okay, because you are working on within that limit only. So population, randomly we are generating in between 0 to 31. Okay. So this is the decimal value of this initial binary equivalent. Okay. Next, we are finding the fitness value. What is your fitness value? It is already given fx equal to x square. There is your fitness value. So we are finding probability. How we are finding the probability, as you know? So this divided by summation of all. 169 divided by summation of all. We will get probability. Simply like that. How you are finding expected count here? See, expected count. So 169. Okay, 169 divided by this average. If you do, you will get it. 0.58. Now you see, so we are getting probability, you are getting expected count. Why? Why you are doing that? So this is all we are doing for implementing the natural selection. Here we are doing natural selection in different manner. You can remember I told natural selection can be implemented in different manner based on the problem you are handling. So here from 0.58 you are getting 1. 1.97 you are getting 2. Yes. And you get approximating 0.51, 1. 1.97, 2. 0.22 approximation 0. 1.23 approximating to 1. What does it mean? It means that, now see the important situation. It means that after natural selection, solution number will be copied in what number? Solution 2 will be copied in 2 number. Solution 3, discard, no copy, 0. Solution 4, copy only 1 numbers. What is now total number of solution after natural selection? It is 2 plus 1 plus 1, 4 only. You will get it. So see how genetic algorithm is encouraging that here 24 is the most fitness value. So it is automatically getting selected in. So these are mathematics only now. We have no control on this. It is automatically getting selected in 2 numbers. Which solution has poor fitness? So that is simply getting discarded. Another fitness, maybe 13 is also low. But 13 you are selecting in 1 copy. 19 you are selecting in 1 copy. Okay, now can you check what is the average fitness value? Average fitness value is 293. So if we check what is the fitness value of this set of solution after natural selection, you will be surprising that is improving. Let us see. So this. So this. So this was the fitness value 293. Okay. Okay. So this Then, so from this initial population, so which population will be shifting? Actually, which population will be copied? See. So this string number 2 in two numbers, one number, 4 one number. So 2 1 4. That means this will be copied in 2 number, this will be copied 1 number, this will be copied 1 number, and this is 0 number. Okay, let me check. Yes. Solution 2 number, 1 and 4 1 number. It's fine. So this is our matching 4. Now whatever you are doing. So we are going for crossover. See, randomly we are selecting 2 chromosomes. Let us say these 2 chromosomes are randomly selected and these 2 chromosomes are randomly selected. And for these 2 chromosomes, crossover point is 4. For these 2, crossover point is 2. Okay, then do the crossover. So 0 1 1 0. Then this 0 will come. This 2. This 0 and 1 interchanging here. Here, these values are getting interchanged here. Okay, so crossover we have done. Then we are finding the decimal values, we are finding fitness. Now see, what is average fitness? 439. So it is improving or not? Yes. So earlier it was 293, now it is becoming 439. Obviously it is improving. So crossover has been done. So after crossover, we will select this pool of solutions. We will bring them for mutation. Okay. This exactly whatever we got after crossover we kept here. Then again from this pool of solution we will randomly select some chromosomes will go for mutation. So randomly selecting this first one, randomly selecting first gene, go for changing. Randomly selecting last one, randomly selecting this gene, go for change. Find the decimal value, find the fitness value. What is the average fitness? 588.5. What was earlier fitness? Earlier fitness was 439. So average fitness is improving or not? Yes, average fitness is improving. So that is our target only. Now, if average fitness value is improving, what does it mean? At least some of the solutions are being improved now. That's why average some of the solutions may be degraded also. But most of the solution is improving in their fitness value. Then only average fitness value is getting improved. Okay. Now, let me show you some important fact actually that as I was trying to convey, many application process are there. So, in particular, yeah. So, in traveling salesman problem, so how to apply and how the concept will be there for this genetic algorithm. See, so that these are the typical concepts already I told for TSP, very well known problem actually. So those particularly who are working for the initially starting optimization techniques are learning, then all of you need to learn this traveling salesman problem, understand it and solve it. If you can solve traveling salesman problem, then obviously you can solve the remaining set of problems. So number of optimization problems are there. So traveling salesman problem is well known among all those. So firstly, you should target to solve this one only. So visit all the cities, one city only once, starting and ending cities same, correct? So these are the cities. Many variations of traveling salesman problems are there. So, we are discussing the most simple one. So, what will be the ultimate result? So this may be a possibility. In this possibility too, if we apply genetic algorithm on this TSP, this will be the ultimate result here. Possible too. So here, remember, our objective is only one. We are not working on bi-objective or multi-objective. We are working only one objective. If you work on multiple objective, then your answer will be different, obviously. Okay. Now see. So the same thing, whatever you are trying to show here, so we are trying to plot it graphically. Okay. So if you plot it graphically, I think in these terms of matrix or graphically, then maybe your solving process may be much more easier. How to, so these are the plottings of various cities. Okay, x-axis, y-axis we have plotted. So now easily you can find out the distance now among various cities. You can use having distance, Euclidean distance, or you can use any other distance mechanism, finding mechanism to compute the distance between the nearby cities. So graphically, you can plot this set of cities in this manner. Here now see. If this is the plotting, now see the situation. So what might be the result? See, this is the result. Check. In this result, what we have observed, let's see. Each and every cities are visited only. Check. Nothing, no cities are left to be visited. All cities are visited. But obviously at most one time only. Nothing is repeated. Okay. Now let's see. So this is a matrix representation of genetic algorithm. Number of representations are possible here. See, distance A to A. A to A, what is the distance? 0. Distance A to 2. A to 2. A to B, what is the distance? A to B. A to B is 2. Distance A to C, not directly connected, na A to C. Not directly connected. That's why you are taking as infinity. A to D, what is the distance? 6. Those who are directly connected, we are considering distance here. A to E, what is the distance? 4 is directly connected. So in this manner also now you can create a distance matrix. I think. And this is the connectivity among all the cities. Now see the situation. This is the connectivity. Here all cities are not connected with every other cities. It is different kind of connection. Connectivity among all the cities. And you need to visit the cities, you need to find the solution using genetic algorithm. Okay. So it will be quite easier for you if problem is like that, situation is like that. Now I'll show an important situations. So what should be the algorithm for this traveling salesman problem? We should initialize the population randomly. What is population? Sequence of cities now, that is a population. Population means set of chromosomes. One chromosome means one sequence of cities, as I was mentioning earlier. One sequence of cities may be our one chromosome. Now, fitness of each and every chromosome. Select parents. Perform crossover mutation. Calculate fitness. Captain to the gene pool. Now, see this. Let us check. Let us assume we have 5 cities, okay? 5 cities. This 0, 1, 2, 3, 4. Salesman is in city 0. He has to find the closest route, shortest route to travel through the all cities, come back to city 0. So what might be the chromosome? So this one will be the chromosome or not? Starting city, closing city is same, traversing all the cities. So this, if I say another chromosome, it might be like that. 0, maybe 4, maybe 1, maybe 2, maybe 3, maybe 0. Okay, this is another chromosome. So as I was mentioning, so chromosome means what? Starting, closing is same, and all other cities would be there in the sequence. In this manner, you can generate multiple number of chromosomes. Okay. Okay. So now once chromosome generated, you can find the fitness value. You know, one way to find the fitness value is the distance. You can find the distance, summation of distance in the sequence. Obviously, you'll get the fitness value. Now, if you want to apply mutation, then how you will apply here? Mutation means sudden changes in gene. But see, if I apply mutation 4, can I make it this 4 to 5 or 4 to 0? I cannot make now because CD number 5 does not exist. If I make CD number 0, then what will happen? CD number 0 will be repeated and 4 will be vanished. Can I do that? I should never do that because traveling salesman problem has its own restrictions actually. So here, the concept of mutation will be different. So what may be done? During mutation, the position of 2 cities in the chromosome is swapped to form a new configuration C. Obviously, except the first and last cell, they should not touch. So here, so 4 and 3 randomly you are selecting and you are swapping. Fine only. So this is your mutation only. Changing randomly the gene values, but within limits. 4 and 2, 4 and 3, these 3 cities you are selecting, okay? And then what you are doing? This 3 is coming here, 4 is going there. That's fine. So this. Now, how crossover you can implement on this traveling salesman problem? Again, this is difficult because you need to keep in mind now that none of the cities should be repeated, none of the cities should be vanished, like that only. So let us see one procedure I can tell. So here in this crossover method, we select a subset from the first parent, then add subset to the offspring. Any missing values are then added to the offspring from the end, from the second parent, that they are found. Okay. So this is your first one, this is your second one. So this, we are selecting a subset, okay? Subset of gene, directly putting here. This subset of gene, okay? See. Then what we are doing? The remaining things now, see, subset of gene, see. So this we are keeping here, just check. This parent we are randomly selected, okay? So this subset of values I want to keep here. Now, if I keep here, values will be repeated now. So I need to take care. So if I want to keep it here, then what I should do? Okay, firstly, let us keep there. Then, see what I have taken. The remaining things, see, start from 9, 8, already there. Don't count. 7, already there. Don't count. 6, already there. Don't count. 5, not there. Syncing the scenario next. Here 4, then we will take 4, 3, 2, 1. In this sequence, which are not there. Okay, simply will be keep on putting all those things. So this is again different kind of crossover actually, what we can apply for this traveling salesman problem. So find out a number of challenges because how to select the initial population. Okay, how to select initial population, then because based on the problem, it will be different, and coding technique will be different. What will be the fitness, how to formulate the fitness function, what will be the encoding scheme for crossover mutation. All these things are very difficult, and based, whatever encoding technique you are using, all these things are depending on this only. So you should be very careful here. Now, there are multiple future research directions for genetic algorithm. So, whatever I told regarding crossover mutation, whatever will be, you can select. So all these things, if you apply reinforcement learning, well-known machine learning concept. If we apply reinforcement learning to determine what will be your fitness, crossover probability, mutation probability, you can do that actually. So, self-adapting genetic algorithm will be there, where you can crossover and mutation rates. You can automatically, it can be selected. And again, that you can go for finding some unique kind of encoding technique, which can be applicable to all the problem, irrespective of the problem nature. That is again a very crucial problem that wherever we can work. Okay. Again, many other researchers has done so many improvements on genetic algorithm. But again, many areas are there still open where we can contribute many things in this genetic algorithm. And if you know this GA concept, then probably you can move to this multi-objective genetic algorithm. There also you'll be finding many more interesting things, which is a little bit complex than genetic algorithm. But if you have some good fundamentals. So today, whatever I focused, as I mentioned earlier, simply I am trying to convey my observations behind this optimization techniques and how it can be applied. Particularly, I showed that for the numerical problems. Okay, now I hope that you got some good concepts on this knowledge on this side. Then maybe you can apply it to solve some interesting real-life problems. Now, this is my contact number, and this is my as well as WhatsApp number. So almost we are approaching to 12:30. So now, if you have any quick questions, I am ready to take your quick questions. Also, I request my participants to please note down my contact number as well as email ID. So this is my WhatsApp number also. So if you have some quick questions, feel free to ask me. Again, feel free to note down your questions in your notebook. So if you wish to contact with me later, feel free to drop me an email, or you can drop me a WhatsApp message so that we can communicate. So as I know, so you will find out many applicability areas, as I was mentioning earlier, for this optimization techniques for your AI, machine learning, and data science. It's a huge open area. Right now, most interesting research are going on. Application of meta-heuristics in machine learning or machine learning in meta-heuristics. Two kind of things are there. So very much interesting kind of things. Okay, so a lot more research works are going on in this domain. So you may focus here also. Then I think by this FDP, you will get a good knowledge on AI, machine learning, data science, and all these optimization techniques. Later you can try how to apply optimization in machine learning, meta-heuristics in machine learning, and how to apply machine learning in meta-heuristics. Also, feel free to contact with me if you want for any collaborative research work. So I am ready for the collaboration. So we can contribute more things. Okay, so I hope all of you have noted my contact number and email ID. Now I'll stop my presentation. So yes. So now if you have any quick questions, we'll take. I feel that was not that much difficult. What about the concepts I was simply delivering? I was delivering from my visualization only. So what I visualize, what I have visualized from this genetic algorithm, how it can be applied to solve some problems. You may note it, you may have seen that from the PPT, maybe I was showing it for your reference purpose only, but whatever I was presenting, the knowledges or thoughts I was sharing, so little bit, maybe that was not written in the PPT. So PPT you may use obviously as a reference purpose. Anyway, so I'm still waiting for some questions, but let me see the chat box. Okay, chat box also, I'm not finding any questions. Okay, then if you have no such questions, please note down your questions and contact me in future. Then once again, I want to thank to the coordinators of this FDP for their kind invitations to share my knowledge on this platform. As well as I want to convey my thanks to the participants of this FDP. So to listen me and to take the headache for that, I think almost 2 hours, started from 10:30, this is 12:30. So thanks on and all. So leaving the session.
Thank you, sir. Thank you very much, sir, for the wonderful session. I hope the participants have got a good insight about the applications on optimization techniques, and they may use these concepts in their upcoming teachings. Thank you, sir.
Yes. Thank you. Yes, please tell them if anyone want to contact with me for any collaborative research work. Since I have already shared my email ID and contact number, please feel free to communicate. Okay. Thank you.
Thank you very much, sir. Thank you.
Thank you. I'm leaving the session there.
Okay, sir. Thank you.